Okay, so recall from last time we were introducing expectation operators, and we did so just with the expectation of x and found that to mean that basically it's just telling us find the mean of the set. That's really it in a nutshell, to just simplify that as much as possible. But now we're getting at this idea of the first central moment, but before I do that, I want to talk about this idea of centering itself, which leads into it. So centering, the formula of which is this. And all this is saying, just simply put, is it's a fancy statistical word for subtracting the expected value or mean from every observed value. So in our case, it would be 1 minus 2.7 out of this set, 2 minus 2.7, and 5 minus 2.7. Note I say observed value, not observation. So that's why I just circle each observed value, even though they have multiple observations in those subsets. So that's centering. So we can calculate these as negative 1.7. This one equals negative 0.7. And this one equals 2.3. Now the idea of the first central moment is saying, great, take our centering values and average them. So now we just want to average all of these. And that's what the expectation operators do, is they average values for us. So this will look like this. We're just literally wrapping the centering equation with an expectation operator. In the formula form, so in sigma notation, we would say, here, I'm going to come down here so you can't see me. This is sigma AI minus the expectation of x, all of that multiplied by, still under the sigma notation, the probability of x equaling AI, where AI represents the categorical value again. So that's saying the entire categorical value, not just an individual observation. So with that, we could take this. We've already calculated all of our AI minus EXs in the centering portion of this. So we're going to take these values, negative 1.7, which is associated with the value of 1, that's the AI in this instance, and then we want to multiply that by the probability of observing that 1 out of the total set. So we get 2 ones out of 10 observations, which is just negative 1.7 multiplied by 0.2. That's going to equal negative 0.34. Then we want to multiply negative 0.7 multiplied by the number of observations, which is 5 out of 10. So the probability of that observation would be 0.5. That's going to give us negative 0.35. Then finally, we're going to come down here. We have the value 2.3, positive 2.3, multiplied by 0.3, because we have 3 observations out of 10. And then that's going to give us 0.69. So when we sum these, because that's what the summation operator is telling us to do now, we're going to get, first, the two negatives will actually combine to negative 0.69, and then we're going to add the positive 0.69 to this. So that'll end up actually zeroing out. And this is actually always the case. So this should happen. Don't fret over it. The reason for it is we want these things to balance. So we have 2 negative terms that should balance out with a positive term, or it's the weights of these terms. So it's not the case that, we have 2 negative terms on one side and a positive term on the other side, as though the number of them matters. What matters is that their probabilistic weight actually balances out to 0. So it's saying that there's an even amount of weight to the left of the center and there's an even amount of weight to the right of the center. That might seem a little just kind of airy right now, but it'll make a lot of sense when we talk about the second central moment, why we're doing this. Before I close out on the video, I do want to talk about one other thing, though. I just want to show this algebraically. So hang on with me 1 second here while I take forever to erase my board. These erasers are top-notch quality. So there's a few rules with the expectation operators that I'm going to give you. So the expectation of a constant is the same thing as just that constant. The expectation of a constant times our x value out of a set is the same thing as that constant times the expectation of x. So you can factor the constant out. The expectation operator of a plus b or minus is the same thing as saying the expectation of a plus or minus the expectation of b. So in linear terms, we can separate things. Finally, the expectation of x is just the expectation of x. So if we were to leverage this information in our general formula for the expectation in our first central moment, we'd start with this. This would be the same thing as just distributing in. So it would be the expectation of x minus the expectation of x, which then simplifies down to the expectation of x minus the expectation of x, which always equals 0. So again, we want this for this. In our second central moment, when we start talking about that, that's where this is headed. We will be squaring these terms in our next video so that we can actually get a sense of what is happening with deviation. Because deviation without squaring balances. But if we square those terms, then we can get some sort of numerical representation of that deviation. So that's where we're heading next time. I will see you guys then.